Thank you all very much for waking up early on the last day of the conference just to see my talk, and also maybe because you cared about the poster awards. So what I'm going to be talking to you today is about the following. First, I'm going to motivate a little about why we care about building a quantum computer. Then I'll talk about why this is difficult, why quantum information is constantly at risk from destruction. Then I'll talk about how you can use codes to protect this information. With that background, I'll talk about my own project, what CodeQuest is and why it matters. I'll present a case study of applying it to study lattice codes, which I'll explain more about later. And then finally, I will present the conclusions of the talk. So, some of you may be familiar with quantum mechanics, others might not. But the thing that's relevant to this talk is that it's fuzzy, it's indeterministic. And in particular, the fuzziness means that it's actually very difficult to pin things down directly. So if you can imagine there's a particle that a system we're examining at progressively smaller scales, you can see that as the scale goes down, the fuzziness of the particle increases. It becomes difficult to pin down exactly where it is. And in particular, if you can imagine a two-chamber system, in a classical system, if you put a ball on one side and you ask, where is it 5 minutes later? Well, it's still there. In a classical system, again, when you're looking at sufficiently small scales, there will actually be tunneling. So the fuzziness of the ball will be such that it will actually cross the border of the barrier you put up. Now, who actually makes things that small? Why should we care? Well, there's a company that most of you have all heard of that works on these things, as well, of course, as MD, who hates being left out. And Intel basically is running this experiment, is trying to pack more and more on their individual cores. I mean, this is just a 2007 core, and you can see how much they packed in an area less than the size of a penny. And the problem that chip manufacturers are increasingly running into is exactly this fuzziness, the fact that the electron is fuzzy, and as you pack your wires closer and closer together, you can no longer be assured that the electron will stay on one wire. It will tunnel. Its fuzziness will cause the current to creep across the boundaries between wires. So, so does that mean this is the end, that this is all we can do? No. We here from the quantum computing field are here to save the day. And the way we are going to do it is by saying, hey, rather than running away from this fuzziness, let's embrace it. Let's embrace non-determinisms. Rather than building a computer based on bits that can be either 0 or 1, why not build a computer whose bits can be both 0 and 1 simultaneously? The determinism of quantum mechanics lets us do this. And the benefits truly come out when you've got multiple bits so that the number of possible configurations grows exponentially. And then using a quantum computer, you actually get a parallel map over all this information. So with one variable, you can do an exponential amount of parallel work. Now, if this seems a bit too miraculous, it is. And the reason for that is because if you actually go ahead and measure the system, what will happen is that one piece of information will be chosen arbitrarily and the rest will be thrown out. So in the terminology of computer science, we get a great parallel map from nature for free, but not a generic parallel reduce. So, does this mean quantum computing is useless? No, because there are problem-specific tricks you can do to get a problem-specific reduce, and it turns out that there's lots of problems, and this number is only increasing, that are amenable to quantum speedups. Most famous, of course, is the factoring problem, which breaks the public security of the internet, but there's lots of other problems. So a quantum computer is useful for there's all sorts of things a quantum computer can do, even if it isn't a miracle machine. So great, why haven't we built one? Let's go ahead and build one. Well, there's just one problem, which is that nature hates quantum computers. Incidentally, it also hates fusion. What happens is that, so all right, you've got your quantum computer sitting there minding your own business. Nature is constantly zapping it with all sorts of horrible noise. And in some respects, even worse, nature will also sometimes creep up to your quantum computer and look inside of it. which is scary because, again, that breaks it. That destroys all the quantum information except for one piece. So what can we do? Well, a necessary but not sufficient part of the solution is to build a shield. The shield will block some of the noisy interaction. It will help you out a lot, but some always manages to get through. So we just have to live with the fact that our pieces of information are subject to random destruction. And okay, so let's live in this world. We know some things about this world in the classical world. So imagine we're dealing with classical bits that are subject to destruction. So what do we do about this? Well, in the classical world, one simple thing we can do is use redundancy, store 1 bit in 3. And then if 1 bit gets destroyed, what you can do is just, on a very regular basis, take a vote. Every bit casts 1 ballot, the majority wins. You assume that was the correct value, you correct it, nature is thwarted from its nefarious attack on your system. So now let's imagine we just took this idea and straightforwardly applied it to a quantum system. In that instance, so one of our bits gets destroyed. Okay, now let's go ahead and perform a majority vote. Unfortunately, you have a problem basically at step 1. So step 1 is figure out what ballot everyone's going to cast. But in order to do that, you have to measure the system. And once you've done that, you've already lost. You've destroyed your quantum computer. Now you just have a classical computer wasting all of your effort. So, all right, what's an alternative? Well, it turns out that what we did in the classical system, there's actually an alternative way to do classical error correction that is enlightening, which is rather than measuring each bit, just ask whether the neighboring pairs of bits agree. If everyone agrees, then no error has been introduced. If, say, the first 2 disagree and the last 2 agree, that means that there's an error in the first bit, and so on. If both pairs disagree, that turns out to mean that 1 and 3 agree. So this allows us to detect which bit has the error and so correct it without having to figure out what bit is stored there. So this is almost good enough, but in order to, but now I need to spend a minute just to tell you about what quantum information actually looks like. So classical information, as you know, is either 0 or 1. And if you're not used to quantum computing, your conception of a qubit, it might be that it's in between quantum 0 and 1 on a line. But that actually isn't true. It actually falls as a point on a sphere. And so in particular, you can see that on a sphere there are no privileged points, and there's also no privileged axis. So this is an arbitrarily chosen axis to be the classical, to line with our classical 0 and 1. But we actually have, like at least 3 orthogonal axes. And you can measure along each one. Measurement will actually collapse you along one of the 2 endpoints of that axis. So for example, if you measure along the z-axis, a +1 measurement means that you've got a 0 there, and a -1 means you got a 1. But you could just as well measure along the x-axis, the y-axis, or anything in between. So there's a lot of structure there. It's more complicated than 0 or 1 or anything in between. So in the context of thinking in terms of measurements, here's how you might define the first code, which is measure each qubit individually, and the I's just mean don't measure anything, so it's like a no-op, and take the product of your outcome. So again, this is bad because it completely collapses our state, removing all that is the essence of quantum from it. This is an improvement, so z times z is +1 if they both agree, that is if they're both +1 or both -1, and is -1 if they disagree. So this is exactly that measurement I talked about where you measure if 2 bits agree or disagree. Now this is an improvement, but as you can see, it only looks for bits along the z-axis. And we've got these 2 other axes to worry about. So we need to improve this, and how are we going to improve this? Well, one thing, the most popular algorithm is the Feynman algorithm, which, as most of you probably recall, is write down the problem, think really hard about it, and then write down the answer. Unfortunately, not all of us have a Feynman around, and so really, but on more philosophical grounds, the problem with this is it requires us to use our head, and as we all know, a mind is a terrible thing to waste. So, thus we introduce CodeQuest, weapon of mass simulation in this war on noise. And the CodeQuest algorithm looks more like this. Step 1, input a choice of measurements, quantum measurements into your system. Step 2, let the computer think really hard about it. And then step 3, output the optimal code using those measurements. Now, unfortunately, in this restricted time, I don't have the ability to explain to you exactly what I mean by optimal, only that it's a very strong condition. It took me a year to prove that it was correct. And let's just say that it's so strong that anyone who attempts to find a better code will always fail, except for Chuck Norris, who will always succeed. So, okay, now this is algorithm. You might say, wait, how does this help us find a code? This only tells us whether a code is good or bad. The algorithm is actually very fast. For 5 qubits, it can examine hundreds of thousands of codes per second. So what you can do is you can start with a huge cloud of choices, and then like searching through needles in a haystack, you can pick out a good one. So you can, this is how you can use this to come up with good quantum codes. So now just to show you an example of using this, we're going to look at lattice codes. And the idea behind a lattice code is this is a lattice. It's basically just a regular graph, and regularly structured graph, I should say. And what we're going to do is we're just going to put physical qubits on the vertices of this graph, and to every edge there will be a measurement, and that's a 2-body measurement that involves the 2 qubits to which it connects. So there's lots of lattices that one can construct. We looked at 9 of the 11 regular tilings, or convex uniform tilings, they are called. And for each tiling, there was some number of possible measurement choices you could pick for that tiling that did not depend on size. So what we would do is we would run our simulations on progressively larger lattices constructed from these tilings, and then look at the scaling properties of the code to see if this was a good tiling to use for codes or not. So this is what our data looked like. Now, this is a very complicated plot, so I'll step you through it. Recall that I said that we're constructing progressively larger lattices, so the x-axis is the radius of the particular lattice we looked at there, and underneath it is the number of qubits in that lattice, which is going to go like the square of their lattice. It's because this grows like an area. On the y-axis, we have the number of qubits you can store in that lattice. In this case, it's boring. It's 1, but you'll see a case later where this number will increase. So for simple codes like the ones I've described, you can only ever store 1 qubit, but for more advanced lattices, you can actually store multiple qubits. And unfortunately, the holographic projector was down today. So rather than putting a 3rd axis on my plot, I had to make use of this notation where the number of sides in the polygon represents the distance of the code, which is related to how many errors can happen between each voting process without you losing the information. So in this code, we only have 1 qubit. No matter how big your lattice is, you can only store 1 qubit in it, but the number of errors you can correct per unit time goes up. So this is the code I found. It's a well-known code, Bacon Shore, although I never knew it had this name since my advisor was Dave Bacon, so I got really confused for a while when people were referring to this code I'd never heard of. Here's another example of data where there's basically 2 kinds of codes that exist on this lattice, a distance 3 code and a distance 4 code. You can tell the distances by the fact that they're all triangles and squares. And here, as you increase the size of the lattice, the number of qubits you can store increases, but not the number of errors you can correct per unit time. So here's here's an example of a distance 3 code and a distance 4 code on those lattices. Last but not least, here's the rhombohexadeltile tiling, which is there in case you are not used to hearing that term. And as you can see, this has lots of interesting structure to it. There's all sorts of codes. There's codes that grow with the number of encoded qubits, and there's codes that grow with the distance. Here's one picture. This is the code with the highest distance. And I'm actually very proud. This picture was actually selected by the Physics Review article as being one of is put in their gallery. So this is what the CodeQuest project is and does. And so now, just to present the conclusions of this talk, first, hopefully I've convinced you that building a quantum computer is a very important project to attempt. Second, finding good codes to protect quantum information is a necessary part of this process. And finally, CodeQuest changes the paradigm for finding codes by essentially, rather than having people look around, think really hard and stumble around looking for codes, it enables the use of leveraging a computer to search for them systematically. And one of the things I just really like about this particular story is that it fits in with the the quantum computing mindset, which is a computer isn't just, a tool that you use, to get an inferior approximation or, like to a problem. It can actually open up the doors to answering questions that you weren't able to answer before by enabling completely different ways of solving problems. So that's actually one of the reasons that I really like this project and why it really fits in with this computational science setting. So thank you very much.